Hello, class. Okay, so we're going to talk about something called Faraday's law. And we can actually demonstrate this very simply. Let's say we take a wire and hook it up to an ammeter. So it's just one loop of wire that there's no power supply connected to this at all. And now let's say, so now I drew this, try and redraw this wire. Let's say this wire is more like perpendicular to the board. So it's coming out this way. Kind of hard to draw that. Now let's say we take a magnet here. We hold a magnet here. And that creates a magnetic field lines. Like something like this, at least over in this region where our coil is. And what is the ammeter going to read? Right now, it's going to read 0. There's no power supply, there is no current in this circuit at all, so nothing's going to happen. But now let's say we take this magnet and move it closer to the coil. And what we'll see is that while the magnet is moving, there's going to be a current in this coil. And so, again, this is a fairly easy thing to do, to demonstrate, but it's actually a very, very profound discovery. Now, this current exists while we're moving the magnet. Like when the magnet was stationary, current 0. When we move it, we'll get a certain current, but then let's say we move it closer and stop. Once we stop, that current's going to go back to 0. So the current only exists when the magnet is moving. Another thing we can discover, if we move it the other way, then we'll get a current as well, but it'll be in the opposite direction. So we might get like a positive current in one case and a negative current in the other case. Now, you might wonder, it takes energy to create a current. Where is that energy coming from? And the answer is, it's coming from whatever is moving the magnet. So, we move the magnet. And, you might think, well, what about inertia? What if we have a magnet that's far away and it's moving, and then it gets close to the coil, and that creates a current in the coil? That might seem like free energy, but of course, it's not. And so what happens is, when the magnet gets close and it's moving, that creates a current in the coil. And the current in the coil creates a magnetic field as well. And so this coil becomes essentially a magnet that will oppose this magnet. There will be a force between the coil and the magnet. And so that would cause the magnet to slow down. So it would be losing kinetic energy. Or alternatively, if you're grabbing the magnet and pushing it, there's going to be a force opposing that due to the creation of this current, which creates its own magnetic field. And so, it's not a source of free energy. If you want to push this magnet at a constant speed, you're going to have to do work to overcome the interaction of the magnetic fields between the magnet and the coil. But, this effect that, it's interesting that this only happens when the magnet is moving. So it's obviously the presence of the magnetic field in the region of the coil that is creating this current, but just the magnetic field existing there isn't enough. It needs a changing magnetic field. Well, it seems to anyway. It seems to require a changing magnetic field in order to create this current. Now, we can do another experiment. This one might seem a little... See if I can draw. Let's say we have a wire, which we form a loop. And let's say we put like something here, like the wire. Like say we have a little piece of material with two holes. So like the wire goes through these two holes. And let's say we create a magnetic field here that's say perpendicular to the board. Now what if we pull these wires? These wires have to go through these holes, and so those 2 points are going to be the same. And so if we pull these wires, what's going to happen is, this circle is going to shrink. And we will see a current as well. So in this case, we have a stationary magnetic field, but by pulling these wires, we're going from this, like here's this, here we've got those 2 holes here that the wires have to go through. But now there's less wire on this end. And yeah, we'll notice that while the area of this loop is changing, we will also get a current. But then we stop and the current disappears. And so in this case, we have a changing magnetic field in the region of this coil that creates a current. In this case, we have a constant magnetic field, but we have a changing area, and that also creates a current. We can look at one further example. Let's say we take our loop. So it's a situation, we've got a loop of wire. Let's say it's a pretty rigid thing. We're not going to change the shape of it this time. We have a constant magnetic field. And let's say that we rotate this loop. We will create a current in the loop in this case as well. So in this case, the magnetic field is constant. The area of the loop is constant. But now its orientation is changing. We're rotating it. And that creates a magnetic field, or that creates a current as well. And so, again, we have, like if we rotate it one way, we'll get a current going in one direction. If we rotate it the other way, the current will reverse direction. And so what is causing these currents? And we can describe all of these phenomena by something called Faraday's law. Now, to figure out what it is that's actually creating the current, just like what quantity is changing every time, like in every one of these cases. So we'll signify that as, the coil is rotating, that creates a current. In the coil. So here we have a changing magnetic field, here we have a changing area, and here we just have the orientation between since we have a loop, we can draw a normal vector that's perpendicular to that. And so there's an angle between this normal to the loop and the magnetic field. And when that is changing, we get a current. So it's orientation, changing field, changing area. And we can contain all that information by defining the magnetic flux. So I'll do it this way, just like electric flux. And so in this case, we'd have to take the dot product of the magnetic field. So this dA vector, that's a vector that the length of it is equal to the area of the coil, and the direction is perpendicular to the coil. So let's look at this case. We have a constant area, and we're not changing the orientation of the coil, but here the magnetic field is changing, and so there is a changing magnetic flux. So So in this case, as long as the magnetic field is changing, then the magnetic flux is changing. Here we have, same thing. We have dA dt does not equal 0. So let's write this way that here we have a changing magnetic field. Here we have a changing area. If you change either of those, you're changing the flux. And in this case, the dot product, B dot dA, we could write this as, in this case, let's do B dA cosine theta. So yeah, the angle, that theta would be the angle between the normal vector and the magnetic field, and because this coil is rotating, this is constantly changing. And so in every case, we see that a changing magnetic flux creates a current. Now, if there's a current, there has to be an EMF in the coil that's driving the current. And so we're finally at a point where we can write down at least one version of Faraday's law. So Faraday's law. So the EMF in a loop is equal to the rate of change of magnetic flux. Now there's a minus sign in front. And again, we're going to talk about that a little bit, but we can ask the question of what direction is the current going to be. So let's actually examine that in one case. So I think it would be easiest if we look at a changing magnetic field. So let's say we have a loop of some conducting material. So it could just be like a wire that's in a circle. And let's say we have a magnetic field into the board. And say that the magnetic field is increasing. So it's increasing into the board. And so the flux is clearly changing in this case. Let's say we have a constant magnetic field in this region. That makes life easier. So in that case, the flux would just be B times the area. So the magnetic field is perpendicular to the area of this loop. So we don't have to worry about cosine theta. And because it's constant, we can take that out of the integral. Keep in mind the flux is not always the magnetic field times the area. Now when you're using Faraday's law, you can draw your loop. This applies to any closed loop. So you need a closed loop in order to define a flux. And we're going to see that, in this case, we have an actual physical loop here. A conducting wire, or it could be like, say, a copper ring or something. But you could also draw a loop in empty space, and we're going to talk about that as well. So if there's nothing there, we're not going to get a current. But in this case, we get a current, and so there has to be an electric field that's driving it. We'll talk more about that later. But now we want to talk about that minus sign, basically. So let's look at our loop. We'll define the loop to just be the actual conductor in this case. That would be the obvious choice. And so Faraday's law should apply here. And let's trace our loop, say, counterclockwise. So we're saying that for our loop, I'm going to write that down. So that's the loop we're going to apply Faraday's law to. I don't want to draw it yet because we're also going to get a current and we want to know what direction that is. At this point, I don't know what direction. It could be clockwise or it could be counterclockwise. So we'll just write down that the loop that we're going to trace, we're going to apply Faraday's law by going counterclockwise around this loop. And by going counterclockwise, our positive direction is then out of the board. So in this case, because the magnetic field is into the board, that means that our flux is negative. Just because we decided to trace our loop counterclockwise, the flux is into the board, so that's a negative flux, and it's decreasing. The magnitude is increasing. And so the change in flux is going into the board. So a change in flux is into the board. If we look at some time later, the magnetic field increases. And so, as time increases, the flux is increasing into the board. And so we can say in this case that the rate of change of flux is negative. Because by going counterclockwise, positive is out of the board because the magnetic field is both into the board and increasing. The rate that the flux is changing is negative. And so the EMF is then positive because we have this minus sign in front. So the EMF is positive, and so that's going to create a counterclockwise current. So now we can draw, so this is the current, which is counterclockwise. So it's kind of like a battery. If we have a battery here, that's going to drive a current counterclockwise. But this positive EMF, positive direction is out of the board. That's the direction that it's going to drive the current. Now, we usually, if we just want to find, like, say, we can say that this coil, it's an actual physical thing, it has a resistance, then we can calculate the current. And generally speaking, if we're talking about currents created by changing magnetic flux, it's called an induced current. Usually we'll want to know the magnitude and the direction of the current. And very often what we do is we ignore that minus sign. There's kind of another way that we can determine the direction of the induced current, and that's something called Lenz's law. We'll talk about that in a second. But so usually we just focus on the magnitude, so rate of change in flux over time, and then we can use something called Lenz's law to find the direction of the induced current. Okay. So one more thing, magnetic flux is measured, we have the units for flux. Should have written this, this would be Tesla meters squared. And there's a unit called a Weber that we can use. We can measure flux in Webers. I think that's just a Tesla meter squared. Yeah, it's lowercase W-E-B-E-R. Spelling here. So that's sometimes a useful unit. But anyways, yeah, it's named after someone. I don't remember his name. No, it was named after somebody. Okay. So, again, we could use Faraday's law to find both the direction and, if we know the resistance here, the magnitude of that induced current. But usually we do these two things separately when we're talking about induced currents. So let's talk about Lenz's law. Now, what Lenz's law says is that, well, let's look at this induced current. Let's look at two cases. Okay, so they're called induced currents. They're created by a changing magnetic flux. So the changing magnetic flux induces a current. But let's forget about that for a moment. Let's just say we have a current in the wire. I'm going to draw two. So let's, those are two separate things. So let's look over here. We have a current going counterclockwise. Let's forget about where that current is coming from for a moment. But this creates a magnetic flux out of the page. You can tell that from the right-hand rule. Or if you have a wire, you put your thumb in the direction of the current. So here, if you look here, if your thumb's in going this way, the magnetic field line will go into the board, here, loop around and come out. Again, if you look at this piece when it's going down, wherever you apply, you put your thumb in the direction of the current, inside the loop, your fingers are always going to be coming out of the board. Kind of a shortcut, just put your fingers in the direction that the current's looping, thumb points in the direction of the magnetic field inside the coil. So in this case, the magnetic field is into the page. Okay, so Lenz's law, what Lenz said, that was the guy who came up with this, is that this induced current will create its own magnetic flux in the region of this loop. So remember, we have a flux here due to this external magnetic field, but once we create a current, that current is going to create its own flux. So the induced current will create a flux. And what Lenz's law says is that the induced current is going to create a magnetic flux to oppose the change in the flux. So let's say, for example, that this is a constant magnetic field. Then we have a constant flux. There's going to be no induced current. It requires a changing flux for an induced current. So let's, actually I should have erased that. So we already established, just using Faraday's law, that the current in this case, where we have the magnitude of the magnetic field is increasing. We established, just using this minus sign in Faraday's law, that creates a counterclockwise current. But now let's apply Lenz's law. So the flux is into the page. And because the magnetic field is increasing, the change in flux is into the page. And so we know that's going to create a current because that creates an EMF. That'll create a current because we have a conductor here. And so the current is going to create a flux itself. And it's going to oppose this. So the induced current has to create a flux out of the page, which would be counterclockwise. So Lenz's law gives us the exact same answer. So the induced current is going to create a flux out of the page. And so it has to be going counterclockwise. That creates a flux out of the page. And so generally Lenz's law is used in cases like this. So we can ignore that minus sign here. Now that minus sign is very important. Because I said, like right now we're talking about induced currents. But what if we have the same situation, except say that there's no ring here, there's no conducting ring, then if you change this magnetic field, you might not notice anything happening. But, you know, if this ring is here, that's going to create a current, and that requires electric fields to create currents. And so those electric fields exist whether or not there's a conductor there to observe them anyways. And so we can actually write a different version of Faraday's law that's not necessarily related to current. It shows a relationship between electric fields and changing magnetic fields. So that minus sign is very important actually. But for what we're doing now, we're not going to worry too much about it. If we just talk about induced currents, we can look at Lenz's law to find the direction of the current. Okay, now I want to look at it's kind of a classic problem here. Let's say we have a conducting rail here, and this is a conductor on top of it. And so, yeah, we have a closed path. We can create a current here. And let's say we have a magnetic field. Let's say it's out of the page. Okay, so we've got this magnetic field coming out of the page. And again, we can apply Faraday's law to any loop. So let's define our loop. I'll use this color here. So this is our loop here. Now what we're going to do is, let's say we grab this rail and pull it. And so it's now moving. We're going to move this at a constant velocity. And so we're pulling this rail to the right. And so we're going to be expanding our loop as we do so. So, you know, Faraday's law works. We don't have to even have a constant loop. The loop itself can be changing. And so that should create an EMF, which should drive a current. So let's actually apply Faraday's law here. The flux, let's look at that. Now, just so you know, I'm writing magnetic flux here, so I'm putting a B. You don't always have to do that. It's pretty obvious which flux we're talking about. You know, electric flux and magnetic flux. So it should be obvious just from the context which one you're actually looking at, but for now I'll write it. Now we have a constant magnetic field. So that would just be B times A. Let's say this dimension here is D. And let's say this dimension is X. So in this case, the area is just the D times X. And so if we take the derivative here, if we look at the rate of change in flux, well, the B and D are constant, so we have BD dx dt. And let's just look at the magnitude of the EMF. Who cares about the minus sign at this point? Because again, we're going to induce a current here. There's a there's an EMF in this loop due to the changing magnetic flux, and so that's going to create a current. So let's apply Lenz's law to figure out the direction of the induced current. So right now, the flux is out of the page and it's increasing. So the change in flux is out of the page. Okay? Now again, if we push the loop inwards, the flux would be it would still be out of the page, but decreasing. So if we push this rail to the left, then the change in flux would be into the page. So even though the flux is out, it's decreasing, so the change would be inwards. But anyways, in this case, because the area is increasing, the flux is increasing out of the page, and so the induced current has to create a flux into the page, which would be clockwise. So again, clockwise current, thumb points into the page. So we're going to get a current that looks like this. And we can check and see if this makes sense using the right-hand rule, because let's look at this rail that's moving. This is a conducting object. It has electrons in here. So what would the force on an electron be in this moving rail? So the electrons are moving along with it. So again, right-hand rule, V cross B. B is out of the page. So the force on a positive charge would be downward. So the force on an electron would be upward. So we know that just by grabbing this and pulling it, we know from that positive charges are going to move down, negative charges are going to move up. Move up, that's consistent here. In this case, the positive charges aren't going to move at all. But the electrons are going to move upwards. That's a current downwards. And so this is consistent with what we know it must be from the right-hand rule. Okay, so we have the EMF equal to B dV. And again, if we know the resistance, we could easily calculate the induced current. But I want to just, let's actually do that. Let's say that the resistance is R. The resistance in this loop. So let's say that now there's a bit of an issue here. As this rail is moving, the current has to travel a longer distance. So R would probably not be constant in practice, because if we move it over, it's got these little extra lengths of wire it has to move through. So to fix that, let's put a resistor here. So if this is like a 100 ohm resistor, adding those little lengths of wires is going to have no effect whatsoever. And so the current, just from Ohm's law, we'd have B dV over R. Okay. Now, let's look at energy considerations here. Now, again, there's a magnetic field that exists. This is an external field here. But by pulling this, you're creating a magnetic field that's going to interact with the magnetic field here. And so you're going to have to do work. These two fields are going to, as you're pulling on it, let's look at this. Let's look at the force, the magnetic force, due to the current in the wire. So here, just remember force. Well, the magnitude of the force is ILB. I'll write it this way. We're just looking at the magnitude. But to find the direction of the force on a wire, you use a right-hand rule. You put your fingers in the direction of the current and curl towards the magnetic field. So there's going to be a magnetic field, a magnetic force to the left because of that current that is created. So even if there's no friction between this moving rail, there has to be some friction, because in order to create a current, there has to be contact there. But let's say we can minimize friction to practically nothing. But as we're pulling this, you're going to feel a resistance because of the interaction with the current that you're creating and this external magnetic field. So you're going to have to do work in order to pull this at a constant velocity. And let's look at the rate that you're doing work. Here, power due to the applied force. So again, so here, we have to have an applied force. Let's just call it Fa. That'll be a little easier. So the power due to this applied force would just be equal to force times velocity. Our power is, well, in general, or we could say, like, in this case, it would be the rate that work is being done. And if we have a constant force, work is force times distance. And so we just have force times velocity. This part here only applies for a constant force. But we'll say we're moving this at a constant velocity. So that will be the case. And so the applied force has to equal this magnetic force, which is given by this. So we have this induced current, which is here. Now the length is d. V is that external field, which is just given, and theta is 0. The theta is the angle between the current and the magnetic field. That's 90 degrees. So there we go. Okay, so that's the power that is applied. And let's plug in this induced current. So I is dBV over R times D times B. We've already used this. Got the direction of the current. So the power that we have to provide, we can just simplify this. We have D squared, B squared, V over R. Okay, and okay, so that's the power, that's the rate that we have to supply energy. And again, this is just a fixed rate. The D is constant, it's just, we set it up that way. We're saying it's a constant magnetic field. We're pulling it with a constant velocity. R is constant, provided we have a significant resistance, because the wires themselves contribute something, but a negligible amount. So, yeah, let's leave it there. This is just some constant power that we have to apply, and that creates a nice constant current here. The current is also constant. Now, where is this energy going? We're putting work into the system. So energy can't disappear. So let's look at, remember, for currents, power is IV, and we have a resistor here. We can apply Ohm's law. V is equal to IR, so power equals I squared R in this case, because there's nothing that can dissipate power in this circuit other than the resistor. Now, if you had a light bulb or something, that would create heat and electromagnetic radiation. But in this case, it's just this joule heating. And so let's find the power. Let's call this PJ. That's that joule heating. So this energy, we're putting energy into the system. And let's find out how much is being dissipated by the resistor. That would be just I squared times R. So we have So let me, all right. Let's actually back up for a moment. Let's go back to this applied force. We have the force times velocity, and I forgot to include this velocity. So the applied force is equal to the magnetic force, which is IBD. I forgot to include this velocity here. And so, yeah, basically we should have had a velocity squared right there. So sorry about that. I kind of copied it down wrong, just neglected this V. So if we plug that in, then we can see that whatever power we're putting in by doing work on this bar to like fight against this magnetic field, that energy is being dissipated it's being converted into heat in the resistor. Because, you know, we have an R over R squared, so these two expressions are identical. And so, yeah, just looking in terms of energy, we're doing work on the system. Whatever work we put in is being converted into heat in the resistor. Okay, so that's Faraday's law. And I think I'm going to have a second video, because right now we're just talking about induced currents, but I want to talk about just like the electric field that's created by this changing magnetic flux. That's a very interesting topic in its own right. So I'll stop this one here and then just have a second Faraday's law video. We can write it in a slightly different form that's more fundamental than what we're doing here. We'll do that in a separate video.